bond length and bond angles, formation of hydrogen gas molecule formed of two hydrogen atoms, each has one spherical s orbital. So we always start with the hydrogen as a simple molecule, hydrogen gas, or H2 as a simple molecule. And from that, we can build up the other popular molecules. So 1s, it means every s orbital is spherical. So two sphericals and two hydrogens. To form a bond, the two nuclei must come closely enough to overlap 4. So how can we make a bond without like every atom is in a distance, a far distance? So they have to come together, close together, and then once the orbitals overlap or touch each other, then now the hydrogen and other hydrogen will form a bond. So this close distance between the two nuclei measured at 0.74% of the angstrom. And the angstrom is the unit used to measure the distance for the bond lengths, angstrom. So once the two nuclei reach 2.74, they can form angstrom, they can form a bond. At this distance, overlap is balanced by repulsion. The overlap is balanced by repulsion between the similar charged nuclei. Okay, so we need an energy to combine these two, let's say, nuclei. So everything will not come to make a bond unless there is an energy, external energy. So that's why we need this energy to put two atoms together and make an overlap. Once they reach to this distance here, hydrogen, they can form the hydrogen molecule. So the resulting molecule contains, now you see the 104 kilocalorie per mole as a potential energy, which is less than hydrogen atoms from which it was made. Okay, so we need 104 kilocalorie per mole to form the H2. So we say hydrogen has a length of 0.74 angstrom, which is for the single bond. The distance between hydrogen and hydrogen is this one. And the strength needed is 104 kilocalorie per mole. Okay, the hydrogen distance need to break this bond. So this amount of energy, which is formed the HH, needed to break down these two atoms and to form atoms again. So the linearity 180 degree in C2H2, there is an angle in the tetrahedral structures measured at 109.5 degree in methane. Trigonal pyramidal, this is all we have to memorize. In the trigonal pyramidal, the angle between the three atoms should be 107 degree, which is in NH3. The water angular shape is at 105. The angle, the bond angle. Of course, we can't do bond angle like if it is linear bond angle between hydrogen, carbon, hydrogen. So let's do it like here. So if there is a hydrogen bond, carbon bond, hydrogen. So now from hydrogen to carbon to hydrogen, the above angle is 180, the lower angle will be 180. So this one, we call it linear on the same line, which can be found in the C2. Okay, let's go to be precise. It will do like this, carbon, hydrogen. So this is now linear of the C2H2 in the alkenes. Tetrahedral, as we said, the bond angles here, we have to memorize. So each hydrogen oxygen length, bond length is 0.96 angstrom. So we can measure the bond length between two atoms, and we can measure the bond between three atoms. Don't forget this. Hybridization affects the bond length. How can hybridization affect the bond length? The sp orbital contains more s character. Closer to a nucleus, it forms shorter and stronger bonds than sp3. Okay, let's remember that's the sp hybridization will do shorter but stronger bonds than sp2, sp3 orbitals. The sp2 orbital is intermediate. So why we started with sp3, sp and sp3? It's just to compare that sp is shorter bond length and stronger than sp3. Okay, so we don't forget this is about if we have sp formation and then compared to sp3, both of them, they have single bonds. Yes, they are single bonded, but so here one electron in s, one electron in p being used to form a bond, a single bond, whereas here one electron in s and three electrons in p being used for the central atom. Don't forget, this is sp for the central atom. Okay, and the sp3 as well belong to the central atom. So the central atom, sp3, used one electron. So this, I just want to be precise that I can leave this one here just to remember, sorry, just to remember that S, we can write sp3, it means s1p3. And here we have s1p1. Just to be precise, just to see how many electrons in the S. It's not 0, it's a 1. So 1 always, it's not needed to write it down. Once we say sp, it means s1p1. And the S1 means it's belong to the central atom. The central atom, here we have two central atoms, but if there is a NH3, if there is a CH4, so CH4 here, it has the carbon used one electron, central atom, one electron in S and three electrons in P. They can form 4 bonds with 4 hydrogens. Whereas in here, sp, in sp, it means there is one electron in S, one electron in P, can form 2 bonds with the other with other atoms. Okay, so either we write S1P1 or SP. Here is S1P3, it means SP3. So now we come to the, so as we said, if we have SP, so the bonds, single bonds being formed here, they are shorter than SP3. Everything is shorter, it means stronger. Now we come to the sp2, which is in between. It means one electron in S. This belongs to the central atom again. The central atom S1p2 orbitals is or orbital intermediate, and it is, and its length and bond strength between sp and sp3. I don't want to add anything, any else, point or dots or something, because this is dangerous. In the chemistry, we don't write anything beside, just to be precise. I know it's the end of the sentence, but we don't leave anything, any symbol beside sp3. It could be misinterpreted. So now the central atom, as we said, S1, P2, it means sp2, is bond length and strength is between sp and sp3. It's been measured by like analytical machines, and the data show this. So not all single atoms are in the same length. Not all the bonds are similar. No, every atom, every molecule have bond length and bond angles. So sp, SCH bond in acetylene. Now look at this. We have two central atoms. So sp for each carbon, the is shortest. In the acetylene, SPS is shortest. So sp belong to this carbon, and the S is the single bond. So it is the shortest in acetylene. sp3, S of the CH bond is the longest in the sp3. So longest, it means single bonds, it means weak, or strength is weak. Now sp hybrid orbital is 50% S, 50% P character in the sp hybrid. So the character, the strength is 50-50. Whereas in sp3, the S 25% character and the P is like 75. Okay. P 75%. Now, the sp2 has S orbital 33%. Okay, I just already written. Has 33% S character, and what? And the rest will be 66% something. Let's say 66% of P character. Okay, doc. So you can work it out here, will be 0.3366, whatever the number. So now the character, or how can we see the of course, the character means they belong to the percentage of the s orbital inside sp will be 50%, and the p will be the rest. The sp3 has 25%. That's what we said. Let's see the s in the sp3 25, whereas the sp2 SO is 33%. So as you see, 33 is more than 25%, and 66 of the P is less than 75%. So now, if you see the in the ethylene, the S character is 25%, the bond length between carbon-carbon, 1.54 angstrom. The double bond here and the triple bond, as we said in the SP, is a 25%. Okay, so if I enter a text here and write SP, and here we can put this here, and that one is here. So in the acetylene, it will be sp2, and in the ethylene, sorry, the acetylene will be sp, the ethylene sp2, and the ethane here will be sp3. So now the percentage, as you see in the triple bond, is shorter, and the S character is 25%. In sp3, you have, oh my God, in sp3, the S character, wait a second. So in sp3, the character of S 25% here, but here the character in the acetylene will be 50%. That's the S character. And the bond length, as you see, the bond length is here is longer in the ethane. Single bond is longer than double bond, sorry. Yeah, is longer than 1.34 in the double bond between carbon-carbon. Triple bond is shorter, 1.2 angstrom, and the strength here is bigger than this, bigger than that. We always know the strength of the acetylene is, or triple bond, bigger than double bond, bigger than single bond. Okay, now if we text something here, at the end, we have a single bond, single. Let's say there are bonds, single bond. If I be precise, bond length for the single bond length. Single will be bigger than double. Will be bigger than triple. So the bond length Now we come to the bond strength. Bond strength, the triple bigger than double, bigger than single. Bond strength. Okay, so that's final. We just leave this. I just color it with the red. Just to be precise. As actually measured, the HOH angle is 105 degrees, smaller than the calculated tetrahedral angle. Where is this? I think this is in water. And even smaller than the angle in the ammonia. Here there are three bulky unshared pairs of electrons compressing the bond angles. The oxygen hydrogen bond length is 0.96 angstrom. It takes 118 kilocalorie per mole to break one of the bonds of the water. So this is all the strength in the water. The angle measured between hydrogen, oxygen, hydrogen is 105 degree. Why? Because of the two lone pairs on the water here, and they are just making repulsion with the bond length. And this bond length will be very stable when they are on 105 degree, far from the two lone pairs. If we examine the figure, we can see the fundamental similarity in shape of the methane, ammonia, and water molecule, a similarity that by the approach we have used stems from the similarity in bonding. So we just here comparing the CH4 single bonds, NH3 single bonds, OH2 single bonds. But the difference here is without lone pairs, with one lone pair, two lone pairs. Okay, we can write this down. Here it has, let's say, lone pair. And here the oxygen has two lone pairs. Okay, so two lone pairs on the oxygen, and there is no lone pair on the methane. So the methane, when there is no lone pairs, the surrounding hydrogens can go with equal bond length, and they are very stable. Each one in the space, carbon, hydrogen to the top, and they are tetrahedral here. The ammonia is pyramidal, and the water is angular. So this is the best shape can stabilize the molecule. The bond length, bond angles, and drawing structures. The carbon-hydrogen shortest bond length associated with sp. So which is 50-50% S and P in ethine. And carbon-hydrogen longest bond length sp3, where in ethane 25%, 75, and the rest will be So the shapes of the molecules and ions from the VSEPR valence theory, expected number of pairs in the bonding, non-bonding, the total hybridization of the central atom, shape of molecule, and example. So if we have two bonds, we can find them. There is non-bonding. The total are 2, and it's sp hybridization for the central atom. And it is linear. So the linearity is in acetylene and in beryllium hydride or dihydrogen beryllium. Now, these molecules possess linear shape of molecule. Now we go to the 3 bonds. There is no non-bonding. There are total of 3 bonds. They are sp2. They are trigonal planar shape, and we can find them in acetylene, trifluoroboron, and the cation methane, or they call it group of methyl group cation, and this is lost 1 electron, so we have 3 bonds as trigonal planar. Whereas if we have 4 bonds, we expected tetrahedral, and the hybridization sp3, no non-bonding, 4 electrons in where? In the ethane, methane, ammonium group, we can find the shape is tetrahedral. Bonding of 3, 1 lone pair, non-bonding, it means 1 lone pair. 4, a total of 4, we need to add this to these 3 bonding, because this will positioned in a way just as a lone pair, as a high electron density, and it will repulse with the other 3. So we have to consider the 1 lone pair. So this is in sp, approximately as sp3. Trigonal pyramidal, in this case, trigonal pyramidal. It's not tetrahedral. They are like sp3 tetrahedral, but here is approximately tetrahedral if we ignore the lone pair. If you ignore the lone pair, it will be tetrahedral, but this lone pair is in a position to the top of the molecule. So, and here it's giving the shape trigonal pyramidal. And the like methyl group CH3 minus, in here there is a 1 lone pair free and 3 bonding. This is a proper bonding, and this is a lone pair. So here is trigonal pyramidal. In water, we have 2 bonds, OH. We have 2 lone pairs, presence belong to the oxygen, and these will repulse the other 2 bonds, and 105 is the bond angle, and it will, we call it angular. The angular, and you see here is the acetylene, which is linear. Here we have trigonal, and we have here the tetrahedral for each one of them. Now, the linear geometry, as we explained in the alkynes, trigonal planar, we can find them in alkenes, double bond, triple bond, double. This is the linear, triple, double bond, trigonal planar, and tetrahedral for the single bond, as in methane. So this is look like a 180 degree. Here each bond angle over 3, you see, is the trigonal planar. And here we have a tetrahedral, which is 4 faces. Summary knowledge, we have like a question, predict the shape of each of the following molecules. Tell how you arrive at your prediction. Ammonium ion, NH4 plus, hydronium ion, H3O plus, methyl alcohol, CH3OH, methylamine, CH3NH2. So here you have to predict the shape of each one of them. So NH4 ammonium is tetrahedral, methane tetrahedral. Here what we have, ethylene tetrahedral each. This is tetrahedral, this is tetrahedral. And here we have a similar, as we said here, we have here the CH3 bromide, okay, bromide methyl a group as tetrahedral, and we have another shape of bromide. You know, the bromide can sit lower or in this position or to the left position. 3 types of bromomethane. So now write a 3-dimensional wedge dashed wedge line representation of each of the following. So this is the wedge, we call it wedge dash and line, wedge dash and line. This is what we call them, the shape. You can do this. And why they use the wedge dashed wedge line? It's for knowing the direction in the space of this carbon hydrogen into the left direction. Carbon hydrogen is to our direction. Carbon bromide to the right, lower direction, and carbon hydrogen to the top direction. So it's like XYZ directions. So you can do that similar to these molecules you can predict for CH3Cl and the others. And here are the answers for each one of them. But here this is the wedge, dashed wedge, and line shape. This is for HNO3. The NO3 is one hydrogen bonded to the oxygen, the rest with double bond N, central atom, and the 3 oxygen around. And this is the linear. Here we have only lines, formula or structure, and you can do the rest. So this is how you find or draw the structure using lines only, Lewis structures. So the alkali metals, if we come to the end of this session, lithium, sodium, potassium, rubidium, cesium, francium. These are the famous alkali metal in group 1. So in the periodic table, electron configuration is NS1. It's like 1s1, 2s1, 3s1. It's ending with this orbital. So we always have one single electron in the alkali metal group 1. Francium 223 is the atomic weight or mass, 87 electrons, atomic number. So the francium would end up with what? With S1 always. Okay, if you put the electron configuration for the francium, you will end up with a number here to the left, and it's S1 orbital. That gives the like the behavior of the atom, and it's very unstable, reactive because of this single electrons. Paramagnetic behavior of the heavier member of the group. Only artificial isotopes of it are known. The longest lived francium half-life is 21 minutes, 21.8 minutes. Because of this single electron, so it won't be stable, And we always give the half-life time for the elements. How long they're gonna stay stable at normal temperature, which is 20 degree and 1 atmosphere. So it will stay stable for 21 minutes, 8 seconds. After that, it will lose or react with anything in the air. Sodium, 2.6% found in the nature. Potassium, 2.4 percent are abundant, available in the Earth biosphere. They do not occur naturally, but in rock salt. So in rock salt, we can find sodium as pure in the NaCl, and seawater, salt in the seawater, and in borax. The borax formula is this one. So most of the sodium can be found in the borax or ORE. KCl found in salvite, rock, and as potash, KOH, or together in sylvanite. So we can find the potassium combination, KCl and NaCl, in the sylvanite. Natural abundance of lithium, rubidium, cesium are small, very, very small percent found in silicate minerals. Sorry. So minerals, spodumene here. And then the alkali metals user and their compounds. So lithium used to manufacture alloys, glasses, ceramic. Large amount of lithium salt in our body damage the central nerve system. Okay. So the lithium is dangerous. Sodium uses in the production of batteries, glass, paper, detergents, chemical industry, etc. Physical property of the alkali metals. Bigger atomic number increase the metal radius, of course. We have bigger atom, radius is big, decreases the metallic bonding. Okay, decrease the metallic bonding because they will be like electrons will be in the higher energy levels. They are very far from the nucleus when they have a bigger atomic number, and they will decrease metallic bonding. Always the valence electrons, if they are near the nucleus, they can do strong bonds or strong metals bonding. But if the valence electrons are in higher energy levels, so we can expect decrease in the metallic bonding, increasing the size of the atom, resulting high ionization energy due to the increase in the nuclear charge. Boiling and melting points decrease from lithium to cesium. Okay. From lithium to cesium. Always in capital letter. So the melting and boiling point decrease from lithium to cesium. Decrease, as we said, boiling and melting point. So we are giving energy to the electrons to escape or to go to a higher energy level. So once the boiling point, the electrons close, it means low atomic number. Close to the nucleus, it means high boiling points. So from cesium to lithium will be higher melting and boiling point, and vice versa. Metal-metal covalent bond decrease from lithium to cesium. If we have the pure metals, alkali metals. So the covalent bonds, always the bond between metal is covalent, sharing. So this bond, the sharing bond, sharing electrons, decrease from lithium to cesium. Again, because it will go to like higher energy level, or so the covalent bond strength decrease once you go to the higher atomic number or number of electrons. If we take the sodium itself molecule, why is not necessary to include 1s, 2s, or 2p orbitals in the molecular orbital interaction diagram for sodium? Why? Because they are fully occupied. If you see, sodium has 11, 1s2, 2s2, 2p6, 3s1, 3s1. So the one electron in S is very important. The others are the core electrons. So these are not included in the reactions. Only this electron in the S orbital, in the last main shell, main orbital, one electron. This is the only electron is responsible for reaction. So one electron from sodium and another one from the other sodium. So they will form bonding between, or they share the bond between sodium molecular orbitals. And here the bond order is 1. Why? Pair of electron minus in the sigma, minus nothing in the sigma star. So it will remain 1 minus 0 is 1. 1 means 2 electrons forming one bond, one single bond. So it's not necessary to include 1s2, 2s2, 2p orbitals in the molecular orbital interaction. There is no need. They are not involved. So only the one involved in the reaction is this single electron from the one sodium and another single electron from the other sodium. So determine, is it diamagnetic or paramagnetic? Sodium 2. Because we don't have any single electrons left, so they are diamagnetic because the electrons are paired. Whereas in one sodium, the one at sodium atom, it's a paramagnetic. But when combined with another sodium, it will become diamagnetic because of 2 electrons in one orbital oppose each other, spinning oppositely. Alkali metals appearance from sodium to rubidium, silver, silvery white, but cesium has a golden yellow cast. All soft, but cesium has low melting point, 301 Kelvin or 27 degree. Because it's unstable, cesium is the higher in atomic number. So easy to break down the atom. Almost room temperature can found as a liquid. That's the cesium. Alkali metal in chemical behavior, all of them, lithium reacts quickly with water. So lithium react quickly with water. One lithium atom with 2 water will give you 2 lithium hydroxide and 1 hydrogen molecule. Sodium reacts vigorously, sodium with water, explosion. But potassium, rubidium, cesium should be handled under inert atmosphere, as they react violently with the ignition of hydrogen produce okay, with the hydrogen. Sodium is used as a drying agent of hydrocarbon and ether solvents. In nature, especially in caves or oceans, conversion of a small amount of sodium by water to sodium hydroxide occurs slowly, and it could react with the silicon oxide to yield sodium silicate. You remember sodium silicate always come down from the cave, from the roof or from the top of the cave, coming down in like swords, and they form very slowly sodium silicate. And it's dangerous to move in these caves. Could fall the sodium silicate and kill people. Alkali metals react with halides, hydrogen, nitrogen at room temperature. So two metals of alkali metals with halogen, it forms the halogen metals. 6 lithium with nitrogen can lead or produce lithium nitride Li3N. Why? Why nitrogen needs 3 lithium? Because nitrogen has 1s2, 2s2, 2p, 3. So the 2s not involved, but the 3 electrons in p can form 3 single bonds with 3 lithium. Okay? You remember that? Nitrogen 7. 1s2, 2s2, 2p3. So this 3 electrons in p, you remember, as I said, the 2s make a lone pair for the nitrogen, and the 3p electrons can react. They are singles in the orbital, and they can react with the 3 hydrogens. Okay? So 3 lithium. 3 lithium or 3 hydrogen, or any 3 of other metals. And now you can see here the nitrogen react with 3 lithium. Metal can react with hydrogen to do sodium hydride or metal hydride. Alkali metals, oxide, peroxide, superoxide, ozonides, all of them group heated with air to produce oxidated metal, and the lithium oxide is Li2O2. Why O2? Because 2 electrons in the p of the oxygen can react with 2 lithium. Okay, doc. Now sodium with oxide will do Na2O2, sodium peroxide, potassium oxide or superoxide will be KO2. So the oxides, white crystals, here pale yellow, rubidium yellow oxide, cesium orange, can be obtained impure by using limited air supply. Again, we have, we can do the potassium hydroxide for another reaction from the KO2, potassium superoxide with water produce sodium or potassium hydroxide. And if you add carbon dioxide, then you will form potassium bicarbonate. Sodium peroxide react with CO2 to give sodium carbonate. And you can see Na2CO3 is very important for the bread, or they call it in the soda. It's very important to use sodium bicarbonate if there is a hydrogen in it, or sodium carbonate. Alkaline earth metal, the last one, is beryllium, the group 2, beryllium, magnesium, calcium, strontium, barium, radium. So you can see the magnesium important for the sharpeners used and as a fire starter and powder, very explosive, and ribbon. And the earliest known alkaline earth metal was the lime. They called calyx, which is known to calcium oxide, used in the ancient time in the composition of mortar. Magnesia is the Latino name or from Greece. Oxide of magnesium was shown alkaline earth metal different from the lime. Scotch chemist Joseph Black observed the magnesia gave rise of the soluble sulfate, whereas the derived from the lime was insoluble. Radium, naturally occurring radioactive metal, very important, formed from the decay of uranium. And thorium in the environment, the most common isotopes. There is an isotopes for the radium as well. We can talk about it later. Okay, thank you for watching.